443.950.
I'd like to say good morning and welcome everybody. Very good turnout here this morning. This is our fourth seminar, and Charter Radio Club sponsors it. Rick Bono is our presenter today, and he's going to tell us about portable end-fed half-wave antennas. The Charter Radio Club President Jerry, KB5TMC, and myself, we kind of ramrod these seminars because we'd like to get people together and we like to learn. So I'm going to turn it over to Rick, and what a Rick.
Okay. Well, thank you, Cliff, and thank you all for coming to join us today. I really appreciate the turnout, and hopefully this will be an entertaining and interesting session here today. So, my name is Rick Bono. I'm from here in Brownsville. My call sign is N05B. Some of you folks may have heard me on the Starlink repeater. One of the things I like playing with, especially, is antennas. And I've already given a presentation on a mag loop antenna that we did. I think that was our first presentation we did out here back in March or so this year. And also did one on a homemade buddy pole. So those presentations, by the way, are on our website. So if you guys want to take a look at what we did on there, they're certainly available for review. Today I wanted to talk about a portable end-fed half-wave antenna, and just about end-fed antennas in general. And you know, a lot of my motivation for playing with antennas is I like to work portable. I like to go out in the backyard and set up an antenna for the afternoon, and try and work the bands on it, or be able to go out to something like the National Park Service, is doing the national parks on the air this year. So being able to go out to Palo Alto or setting one of these things up is something that interests me. So I'm always looking at a way to get an antenna up fairly easily, something that's effective, and being the lazy man I am, I like something that goes up pretty quick. So my goal here was to develop a portable end-fed half-wave antenna, something that's easy to deploy, something that has multi-band capability. I'm also looking for something that was resonant, so I didn't have to use an antenna tuner out in the field. And power handling, I use an MT817, but I also have an amplifier for it. So when QRP just isn't getting it out, I'd like to be able to run at least 45 watts on it with the amplifier I've got. Ideally, I'd like it to run between 40 and 10 meter without having to go through too many gyrations for changing bands. I'd like to reference a lot of what I've got off this presentation today comes from Steve Yates, AA5TB. He's a fellow Texan here that has done a lot of work on both mag loops and end-feds. Really good information there if you want to really get into depth on the subject. And I'd like to give him a lot of credit for some of the stuff in this presentation. So I'd like to start by talking a little bit about the dipole antenna. And we're all very familiar with the center-fed antenna. The key of having the feed point in the center is that, as you can see from this graph, our voltage will be at a minimum, but the current is at a maximum. So if we remember Ohm's law, V equals IR, right? So V over I gives you the resistance or the impedance in this case. So in this case, we have a very small voltage with a very high current giving us a low impedance. So typically for a dipole, that's around 72 ohms, right? That's great for when you're trying to match up with a rig that's in a 50 ohm, looking for a 50 ohm load. But what happens as we move away from the center? As we move away from the center, the current starts coming down, the voltage starts going up. So by the time we get out here to the end, our current is really at a minimum, and our voltage is now at a maximum. So if we look at that equation now, we'll see that we're starting to look at impedances that are in the 1800 to 5000 ohm range. So clearly that's going to be a problem matching to a 50 ohm, to a rig expecting a 50 ohm load. Given that, why would we want to use an end-fed wire antenna? The main thing is for a portable antenna, it does simplify the deployment. And meaning that, for example, in a vertical, all I have to do is send the end of the wire up to the top here. If this was for example, an a vertical dipole, somewhere here at about 30 feet, I'm going to have to come out with my feed point, and I'm going to have to bring it out as perpendicular to the radiator as possible for a ways to ensure that that I get proper matching. So not only sending the end of the wire up, but also having to support the feed point about 30 feet off the ground starts getting a little onerous. With the end-fed antenna, all I have to do is send the end of the wire up, and my feed point's down here on the ground level where I can work with it fairly easy. The other nice thing is you can deploy these in ways that we're very familiar with in terms of different dipole configurations. You can use the inverted L, you can set it up as a sloper, half square, inverted V. The inverted V only needs to support the wire once again. It's not supporting the feed point or the feed line. The feed line will be down in here somewhere. I don't go into much about pattern and gain in this presentation because basically the pattern and gain is going to be the same as however you configure this antenna. It'll follow a dipole gain and pattern matching. So the real key here is that you have the feed point down in the ground here where it's at a convenient point to work with. You don't have to worry about supporting the feed lines up high in the air. By the way, we've got it set up just outside right now. We have it up on a 30-foot travel mast. The end of the wire is up about 30 feet. So there's actually two types of in-fed antennas, okay? There's a non-resident approach. And for the non-resident approach, what we have to do is first match the high impedance of the feed line with a 9-to-1 unun. Okay, so essentially it's a 9-to-1 transformer here. And that's to bring that high impedance of the feed point down to a level that's manageable for the rig. But it's non-resident, so it's very important that the length of wire you use is not a length that is halfway multiple of any frequency you tend to use. Now, once you get onto the, let's see if this actually works. This website is kind of handy because it gives you links to avoid for different configurations. For example, here, if you want a 40, 30, 20, and 15 meter non-resident antenna, you need to avoid links that are in these red blocks. So, about 35 feet would be okay, 40 feet would be okay. 66 probably wouldn't be a good idea. And that's because those are multiples of the frequencies of these bands. The other thing is, this is multi-band, but you'll need a tuner, and you'll need a tuner on all bands. So that's something that's a requirement for this. I actually have, as my base home antenna, I have an in-fed non-resident antenna that I've been using now since I got my ticket about 2 years ago. So it's actually worked out real well for me. I've got it's a 53-foot wire. It's strung up horizontally about 20 feet off the ground, and it's been working really well for me. So I do start getting the itch for a little gain every now and then, but for just everyday use, it's been a really good antenna. But I do need to run it with a tuner. If you guys are interested in building one of these antennas, the definitive website is by the Emergency Amateur Radio Club in Honolulu. They used to actually sell this, but the instructions on building one of these things are really clear. I would definitely recommend you looking at this, winding the toroid for the matching, building the little matching box. Essentially, you have the wire coming in on one side, you have the ground coming in on the other, and then your feed line coming in there. So about as easy as it can get. Just hang a wire anywhere between about 24 and 60 feet, and you're on the air.
How much of the toroids?
Depending on the size, right?
No, that one there.
How much is that toroid?
Yeah.
I'll tell you exactly.
Approximately.
Let's see what it is. Materials here, let's see, it's a T130-2. I would say it's about $8, $8 to $10. So these are the components of a in-bed half wave. We have the half wave of wire, half wave length of wire. We have a very short counterpoise as a return. In the case of 20 meters, this counterpoise is only about 3 feet long. And interestingly enough, without that 3 foot of counterpoise, it just won't work. If you take it off, it just won't work. The rest of this is composed of a toroid transformer with a secondary and primary. There's N-to-1 turns. I'll talk a little bit about that as well. And then a capacitor here, which is used to tune out the inductive reactance so that it is resonant at the frequency of interest. All that hooked up to a 50 ohm coax. So we're going to use a toroid with a 9-to-1 turn, N-to-1 turn between primary and secondary. The capacitor should be selected so that it allows it to resonate at the operating frequency with the inductance that you select here. And I'll go into a little more detail on that. And the capacitor is going to need to be a fairly high voltage capacitor if you're going to run more than QRP power levels. It's not as bad as what we've seen before as needing for a magnetic loop antenna, where magnetic loop antenna needs at 100 watts, it needs a capacitor that's rated about 4.5 kilovolts or so. In this case, you need something that's around 600 volts. So it's a little easier to maybe source a cap that'll meet that range. So time for a little math, right? Okay, we've seen that right in here, we have an LC circuit, capacitor, and an inductance. It's an LC tank. So this is our equation. FO here is going to be the frequency that we want to operate in, and then you can calculate either the inductance or the capacitance based on the values that you have available. To simplify all of this, this may not look too simple, but it's a spreadsheet, and we're going to include this on the website so you guys can play with it a bit. But I basically put together this spreadsheet, and it was really for my own use and not so much to be user friendly, but I'll walk through it here a little bit. In this case, these are the parameters for 3 different types of Amidon toroids. This is the inductance. I'm not sure what they call it. AL, I think it is. It's something related to the inductance per number of 100 turns or something like that. The capacitor I have is a variable that goes from 9.5 to 310 picofarads. So what I've done here is, first of all, calculated the inductance based on the different toroids. I ended up settling on this T94-2. So if I put in 18 turns for my secondary of wire on this toroid, I'm going to end up with an inductance of about 2.7 microamps. So I can take this inductance now and calculate what my frequencies would be given the min and max capacitor range I have. So I was looking for 40 to 10 meters, so this tells me I can go from roughly 5.5 to 31 megahertz. That would pretty much meet my requirement of going from 40 to 10 meters. So then here, I'm looking at different options for the primary turns. If I do 2 primary turns with 18 secondaries, I end up with a 9-to-1 transformer ratio, which tells me the impedance at the terminal should be about 4 k ohms. So that's what I settled on. Essentially, this is where I figured I'd get the best range out of that cap. I'm using this Amidon T94-2 with 18 turns of wire as a secondary, and then 2 turns as a primary. So in terms of capacitor selection, we have to have a capacitor that selects a voltage that allows our operation at the power range we want to do, and also that has a range that will allow us to tune what we're looking for in terms of band operation. You can use a fixed capacitor. You can do this calculation, come up with a fixed capacitor, and operate in one band. So it's not really necessary that you do a variable unless you're going to want to work multi-band operation. In this case, we need to handle about 650 volts for a 100-watt operation. What I'm using is a new old stock Alps variable capacitor that I got from eBay. These are, for some reason, they're shipped from Thailand. They cost $12.50. It was surplus from some of my early mag loop experiments. Clearly not suitable for more than a QRP mag loop, but for this application, it works really well. And just to go into a little bit more detail on the capacitor voltage ratings, you can kind of use this chart to gauge where you need to be for a different power range. 100 watts, you need about 686 volt rating for your capacitor. If you're going to run QRP, you can get away with a much lower voltage rating on the cap. And if you want to run, kilowatt range, then you're going to need a fairly hefty cap to run it. So a little on the toroid now. What I'm finding is Amazon is your friend, right? And I say that because their website here has some really great specs, and I strongly recommend you peruse that website, look over some of their specs. If you guys have ever thought about winding a toroidal inductor for a filter or for some other homebrew project you got, these guys have all the information you need to select the toroid you need, the type of toroid, how many turns of a specific gauge wire will fit on a specific size toroid. It's just got a whole bunch of really useful information that you can plug in there. And I found that a good source for these Amidon cores is a company called Ultronics. They pretty much carry all of the Amidon stock there. You can buy them fairly reasonably priced and get whatever cores you need for these projects.
Here's one thing to note, that Ultronics, there's two different companies with virtually identical names, but you're getting the right one.
Exactly. Use this website. I know that's the right link.
Yeah.
There's one that's ALtronics.
Yeah.
Yeah, I know. Yeah, exactly.
Well, there's another one with ALL-Tronics.
That's very true. There are two different sites for that.
They were partners at one time.
Were they? Okay.
Kits and parts those all the time.
Exactly. Yeah. So, I mean, there's other sources, right? But I found that this was helpful in that, they generally had what I'm looking for, and the shipping was pretty reasonable too. So, something to remember when it comes to these toroids is that for a fixed number of turns, the larger the core diameter, the greater the inductance is going to be. So keep that in mind. If you start getting into trying to use a too big a toroid for a given number of turns, your inductance is going to go up, so if your tuning for the capacitor is going to change. It's just something to keep in mind. I'm recommending using type 2 powdered iron cores for the mesh. I found out the hard way that a type 43 is not going to work. The inductance of the primary is too high to tune. If you recall, I was looking at about a 2.7 microhenry inductance for that Amidon core that I used, the type 2. The type 43 ended up with 500 microhenries, which just completely unable to tune it with the range of cap on it. So once again, I selected a 9-to-1 ratio on a T94-2 core. I'm using 18 turns of the number 22 magnet wire, insulated magnet wire for the secondary, and 2 turns for the primary. The inductance ends up being about 2.7 microamps. This is just a quick view of the parts as I started putting it together. I just mounted it all in this little plastic project box. I've got the cap, the toroid, and a connector. It's not hard to wire these things up once you have the toroid wound. You just basically wire the primary across the capacitor terminals and also a set of banana jacks, and you're good to go. This is the finished unit, and I'm actually testing it here. This quote by Steve Yates is really a key here. To get maximum success off of one of these antennas, he recommends basically putting a resistor across the terminals and finding the resonant point on the capacitor in that way. So if you look here, essentially I've got a 4 k ohm resistor, which that spreadsheet gave me the value I needed for that. Okay, now that we've got our caffeine break, back to a little discussion here about matching this. Essentially, you put a resistor here. In my case, it was a 4 k ohm resistor. Set up my antenna analyzer, set my frequency to my first band. So you'd set it, in my case I was trying for 40. I didn't quite get 40 meters tuned in, but I did get 30. So I'm starting off at 30. You set the frequency of your antenna analyzer to where you want to zero it. And then you adjust this capacitor until you achieve a zero reactance so that you know that you're at resonance. And what I do is just put a little pencil mark or a little pin mark where the knob tunes in at that level. And then you just repeat it for each of the other bands. So I have the bands marked here, but I haven't really tested this, haven't had a chance to test it out on some other bands. I've got this set up for 20 meters. So. But that's the basic procedure for setting up where the band position should be on this tuning knob. For reference, if you use a different tuning ratio or different turns ratio, the resistance that you need to use for that calibration will change a bit based on this formula here. So then my final trimming, start with a dipole, the classic dipole antenna length formula. I came up with 33 feet on 20 meters. I'm using number 22 insulated speaker wire, so I'm not using anything really fancy. It's really fairly light wire. I cut the counterpoise to this length divided by 10, or about 3.3 feet. Attach both to the match box and set up the antenna in the desired orientation. There's a little trick there in that if you're going to tune this antenna vertically, for example, but then you set it up horizontally or you set it up in a different configuration, your tuning will probably shift a bit. So, I set this one up vertically. I've got a setup where I can set that up vertically, and it seems to be working fine with it. Once it's set up vertically, it's repeatable. It seems to be very repeatable at that band. I mean, Cliff, how long did it take us to get that set up out there? I mean, we tuned it in less than a minute, didn't we? Right.
Say a minute.
So I can, use an antenna analyzer to measure the frequency. Trim the wire down until you show zero reactance at whatever frequency you want to tune it at. Now, key here is that the SWR will drop as you trim, but you're not so much interested in minimizing the SWR as you are in achieving that resonance frequency. You want to make sure your reactance is zero, even if your SWRs are 1.5 or 1.6. You're still going to run okay. But the key is to get it to resonance. So here's a look at the SWR as I was trying to tune it. And you can see I did achieve a 1.1 SWR. And when it gets to zero reactance, it tends to stay there for quite a part of the band, which is really nice because it tends to be a fairly broadband antenna. This is just an example of how I deployed it. I've got a 30-foot travel mast that I basically lashed to a hurricane fence post. The wire goes up 30 feet, and my feed point, you can see, is right at the ground level. My counterpoise is sitting on the ground. I wrapped 6 or 7 turns for an air coil choke here. I haven't talked much about the common mode currents that happen on an infit, but you really need to choke your coax in here, or you could bring RF into your shack or up to your rig. That can be a problem with infits. So since I'm running portable, 6 or 7 turns of coax, just quick bound on there seems to do a pretty effective job of choking it off. This is my portable rig setup. You can see part of it out here right now. I have a little solar system out here. I run it with a couple of gel cells. I've got my rig, my amp, and there's the travel mast. This is the whole station ready to transport. So it's a fairly small setup that I can take out and run in the field on solar power. So
Let me back up a point.
I'm sorry?
Common mode choke, don't scatter wind.
No.
It should be linear wound.
Yeah. Well, that's one way to, definitely.
Because if not, the first coil might touch the last coil and do you no good at all.
Well, that's true. I mean, you've got to take some care in the way you
Wind it linear.
Anecdotal evidence, but these were the stations that I worked during my initial testing. I took it out on a Saturday afternoon about a month ago, and I tested it with 45 watts on it. I made 16 contacts during the Washington QSO party, and I made 2 DX contacts into Brazil and Costa Rica on SSB. No real difficulty making contacts. I noticed that in the afternoon when propagation started opening up into Europe, I was hearing stations coming in very clearly from Europe. They were coming in. I wasn't able to really break any pilots because there were some big guns out there that day. I have noticing that the background noise is pretty low on this antenna. It seems like it's got good ears. I mean, I can really pick up some stations on this thing. Talked a little about multiband. So how can I make this antenna a multiband antenna? Well, the secret would be to use some links. Essentially, I break the wire up. If I'm going to operate on 40 meters, I have a wire that's going to be tunable to 40 meters. But if I'm going to run at 20, I can open up this link here, and now this is the only part of the wire that's actually going to be resonant. And likewise, if I want to run at 15, I'd open up this link here. So essentially, by opening those links and then changing my capacitor value, I can get this antenna to work multiband also without a tune. So it's fairly straightforward to be able to set that up. Just a little more time intensive for the first setup to, make sure you got your wire links correct and such. But it is a fairly effective way to make this work multiband. So the basic design goal, I think, was met, and it is easily deployed. We spent all of about 10 minutes getting the whole thing set up, and about 8 minutes of that was Cliff pounding some stakes into the ground. So it is easy to build. It is low cost. It gives you a lot of deployment options, and they're fairly simple deployment options. So if you're going to work out in the field, if you're going to go out on field day, if you're going to work national parks, this antenna would be really simple to set up. There are some future work I want to do. I want to get these links set up. I do want to redo the matchbox to reduce the stray capacitance. I think I've got a little bit too much stray capacitance in my wiring, which has reduced my tuning range. So I really want to get 40 meters working on this thing. So that's one of the things I'm doing. Now, while we've been talking here, and since we set this up, we've been running Whisper. And been running 20 meter Whisper. In fact, we're transmitting right now. And those are the stations that we've contacted in the time we've been out there, including Australia. And that's on F1. So,
No, leave there for a second.
yeah.
What time period is that, Rick?
From the time we set it up out there,
About the last hour?
about the last hour.
Question I had was on the,
Cliff's hearing
Yeah, but I'm not. Wow. Oh, wait a minute, no, this is 20, right?
This is
It's not
20,
40.
yeah, this is
Okay.
20.
If you went to 40, I'd be here.
Let's see.
Cliff has to hear everybody because he's number 3 in the world now. We gotta bow to him when we go near him.
So that antenna heard that BK station, but so I heard that station, it didn't hear me, so just to give it some reference. So.
do you have any idea what the angle of radiation is off of that?
Should be whatever you get off a vertical in the same.
Just a regular half wave? Okay. The other question I had is on that counterpoise. The counterpoise you show as being like 3.3 feet for 20 meters. But if you go up to 12 meters, do you have to shorten it or just leave it alone?
Well, you should, but really you don't have to. You really don't have to for this kind of thing. I mean, theoretically, you wouldn't want to change it to a bit of a longer one. But I think in practice, as long as
It's
you have
only like that long.
I think in practice, it doesn't really make much difference.
Okay.
But I know if you take it off, it does not.
Anybody else have questions?
Well, thank you very much. Appreciate it.
Thank you.